Very good morning to one and all. I'm Professor M.S. Patil, and in this video lecture, I'm to talk about introduction to shafts. Starting with the learning objectives of this session, today we are going to see what is shaft, and we will talk about the different types of shafts, and then we will discuss about the different materials that are used for manufacturing the shafts. Starting with what exactly is a shaft. The transmission shaft, as it is called, is a rotating machine element, essentially circular in cross section, and which supports transmission elements like gears, pulleys, sprockets for transmitting the power. The shaft is always a stepped shaft with maximum diameter at the center or in the middle portion and minimum diameter at the two ends where bearings are mounted. The steps are provided on the shaft in order to support the rotating element or rest the rotating elements like gears, pulleys and sprockets. Keyways are provided on the shaft in order to prevent the relative rotating motion between the shaft and the hub of the gear or the pulley. The minimum diameter, as it is seen over here, where the bearings are mounted, is the calculated diameter, and we can have additional diameter at different portions. So, talking about the different types of shafts. Shaft can be an axle, but axle is not a rotating element, but which supports the rotating elements like wheels, hoisting drums, or rope shoes, and which is fitted to the housing by means of bearings. Here we can see the animation of a bicycle. The rotating wheels are mounted on the axle. So, axle is a non-rotating shaft which supports rotating wheels in this case. A shaft can be a spindle, which is a very short in length and which is generally an integrated part of a machine tool. Spindles are generally lathe machine spindle, drilling machine spindle. So we can call them as the integral part of the machine tool. You can see over here, a chuck is mounted on the spindle and the chuck is supporting the workpiece. So a spindle is nothing but it is a short length shaft. When we differentiate between an axle and a spindle, then axle is a non-rotating element while a spindle is a rotating element. Next, a shaft can be a counter shaft. So it is nothing but a secondary shaft which is driven by means of main shaft and from which the power is supplied to the machine component. In this case, we can see an input shaft is over here. On the input shaft, an input gear is mounted, which is rotating this shaft and this shaft, which in turn rotates the shaft B. So these are the counter shaft where we can transmit power from input shaft. So these are called as counter shafts, and generally we find the counter shafts in the gearboxes. A shaft can be a line shaft. Line shaft are nothing but they are connected. N number of shafts are connected in axial direction by means of coupling. So when we have to transmit power simultaneously to different machine tools, then we are using line shaft. Right? There will be an electric motor which will be driving the main shaft, and the other shafts will be in line with the main shaft which are connected by means of couplings. So these are called as line shaft. So we have seen a shaft can be an axle, it can be a spindle, it can be a counter shaft, or it can be a line shaft. Now, talking about the shaft materials. Now, the selection of the materials for manufacturing the shaft is based on the properties which are desired. Generally, the properties desired for a shaft material are: it should be ductile in nature, it should have a hard surface and a tough core. That means toughness is again an important property. In many cases, shafts are subjected to fluctuating loads. Therefore, fatigue resistance is also one of the important property. Again, the shaft material should be capable of taking the shocks and vibrations coming. So, depending on these properties, we can use different types of materials for manufacturing the shafts. Ordinary transmission shafts are generally made up of medium carbon steel with a carbon content varying from 0.15% to 0.4%. For example, we can have 30 C8 or 40 C8, which are generally called as machinery steel. Here 30 C8 means 30 divided by 100, that is 0.3 percentage of carbon content by weight, and 8 divided by 10, that is 0.8 percentage of manganese. Here one thing should be noted, that manganese is not purposefully added in the steel, but it remains as an impurity, and therefore we cannot call it as a alloy steel. We are calling it as a plain carbon steel with medium carbon content. Again, if the amount of strength desired is more, then we can go for high carbon steel, because high carbon steel imparts hardness on the surface, and therefore we can go for higher carbon content, that is 0.45 or 0.5%, if the amount of strength is required is more. Again, for greater strength and special applications, we can use alloy steel, which includes nickel chromium, and molybdenum as an alloying content in the shaft. And the most common type of alloy steels which are used for manufacturing the shafts is 16 Mn 5Cr4 or 40 Cr4 MO2, and likewise. So nickel, chromium, and molybdenum are the common alloying contents in these alloy steels. Why chromium? Why molybdenum? Why nickel? Generally, chromium imparts corrosion resistance, and molybdenum, when it reacts with the carbon present over there in the steel, it forms carbide, which imparts hardness to the steel, and therefore where the desired strength is more, we can go for alloy steels. There are certain advantages of alloy steel as shaft material over plain carbon steel. Plain carbon steel means medium carbon steel or high carbon steel. Alloy steels, though they are costly compared with plain carbon steel, they have the advantage of having higher strength, hardness, and toughness. Again, high values of hardness and strength can be achieved for components with large section diameters. Alloy steel possesses high resistance to corrosion. As I have already told, chromium is purposefully added to steel for improving the corrosion resistance property. And therefore, if we are getting high strength, hardness, and toughness for the application desired, then cost can be justified over these advantages. Now, when we are talking about the design of shafts, Shafts are generally designed on three different bases. One is on the basis of strength desired. That means here the amount of stresses getting induced in the shaft material due to application of external forces. If that induced stress is less than the permissible stress, then we can say that the shaft is safe on the basis of strength. Again, shaft can be designed on the basis of torsional rigidity. Torsional rigidity means the angle of twist when the shaft is subjected to torsional moments or simply torque or twisting moments, then it gets twisted. Then that angle of twist, if it is within the permissible limits, then we can say that the shaft is safe on the basis of torsional rigidity. And we can also design the shaft on the basis of lateral rigidity. If the amount of deflection due to the external forces acting on the shaft, if the amount of deflection is within the permissible limits, then we can say that the shaft is safe against this criteria, that is of lateral rigidity. So talking about the design of shaft on the basis of strength, generally shafts are subjected to axial loads. They are subjected to twisting moments due to transmission of torque, and they are also subjected to the bending moments due to the weight of the gears and pulleys mounted on the shaft, or due to the resultant forces due to meshing of gears or transmission of power from one pulley to another pulley. Then the shafts are subjected to bending moments. So we have to design the shaft on different bases. So shafts can be subjected to axial loads. So we have to talk about the safety of the shaft subjected to axial loads. Shafts can be subjected to bending moments due to external forces. Shafts are subjected to twisting moment due to transmission of torque. Shafts can be subjected to combined bending and twisting. This second and third criteria can be combined. So when combined loads are coming on the shaft, we have to talk about the different theories of failures. And generally, two theories of failures are used for design of shaft. One is principal stress theory and one is maximum shear stress theory. Again, there are certain codes for design of shaft, and one such code we are commonly using, that is shafts are designed on the basis of ASME codes, where we are designing the shaft based on maximum shear stress theory only. That we will talk in our next video. So these are the different bases for the design of the shaft. In the next lecture, next video, we will continue with the formation of equations for the design of shaft based on these different criteria: strength basis, torsional rigidity basis, lateral rigidity basis, and subjected to axial loads, bending loads, torsional moments, and combined bending and twisting. Thank you for now. Thank you for listening this video very patiently. Have a good day.